Let me ask you something before we even start. Have you ever held a drone in your hand, felt how light it is, looked at that tiny battery clipped underneath, and wondered how on earth does this stay in the air? It weighs almost nothing. The battery powering it weighs more than half the machine. And yet you push one stick forward, and it just leaves. It climbs into the sky like gravity forgot about it for a second. Doesn't that bother you a little? It should. Because that's how is one of the most beautiful pieces of engineering you will ever take apart. And here's a bigger question. Why is it that right now, today, armies are spending billions on these things, farmers in Punjab are spraying their fields with them, Hollywood is strapping $40,000 cameras to them, and a company like Amazon is seriously trying to drop a parcel on your doorstep using one? Soldiers, farmers, filmmakers, delivery guys, what do those four people have in common? Normally, nothing. But all four of them looked at a drone and saw the future. That's strange, isn't it? That's worth understanding. So let me push you one step further. Could drones become as common as smartphones? I know. It sounds like hype. But hold that thought, because I genuinely think the answer is yes. And by the end of this video, I think you'll agree with me. Welcome to Droneverse. This is the series where we don't just fly drones, we actually understand them. We open them up, we break down the physics, we look at how the whole world is regulating them. And we do it the way I teach it if you were standing right here in my workshop with a screwdriver in your hand. This is Chapter 01, Drone Fundamentals and Flight Physics. Think of today as the foundation. Everything else we build in this series sits on top of what you learn in the next 40 minutes. And let me be honest with you about why this matters, why I'm bothering to make this, and why you should bother to watch it properly instead of half listening while scrolling. Learning drones today is a lot like learning computers in the 1980s. Think about that. In the 80s, most people looked at a computer and thought, that's a toy. That's for nerds. What am I going to do? Type my grocery list? And a small group of people looked at the exact same machine and thought, this changes everything. Guess which group ended up running the world for the next 40 years? Drones are at that exact moment right now. They look like toys. Some of them are toys. But underneath, there's an industry that governments are pouring money into, because whoever controls the airspace, cheaply, safely, at scale, controls a huge slice of farming, logistics, defense, mapping, and emergency response. Let me give you the real picture, not the brochure version. In India, farmers are using drones to spray pesticide over an entire acre in about 7 minutes, work that used to take a man with a tank on his back the better part of a day, breathing in chemicals the whole time. That's not a gadget. That's a health upgrade and a time machine rolled into one. In the military, surveillance drones can loiter over an area for hours, silently, watching, without putting a single pilot at risk. That capability has completely rewritten how modern conflicts are fought. Amazon and a dozen other companies are running real delivery experiments. Drop the package in the backyard. No truck, no traffic, no driver. It's not everywhere yet, and there are good reasons for that we'll get to. But the prototypes fly today. In search and rescue, a thermal camera drone can sweep a hillside at night and spot the body heat of a missing hiker in 20 minutes, a search that would take a human team an entire freezing night and might fail anyway. Engineers use them to inspect bridges, cell towers, wind turbines, and power lines, climbing 200 feet so a human doesn't have to dangle off a rope to check for a crack. And, my personal favorite, those jaw-dropping drone light shows, where 500, 1,000, sometimes 10,000 drones paint a moving picture across the night sky. Every one of those dots is a flying computer holding its exact GPS position to within a few centimeters. That's not magic. That's the stuff we're about to learn. So here's my promise. If you stick with me today, you will never look at a drone the same way again. You'll see the forces, the physics, the brain inside it. Let's go. Okay. First question. What is a drone? And before you answer the flying thing with 4 propellers, let me stop you. Because that's like saying a car is the thing with 4 wheels. Technically true, completely missing the point. Here's the cleanest way I can put it. A drone is any aircraft that flies without a human pilot sitting inside it. That's it. That's the heart of it. No cockpit, no person on board. The pilot is somewhere else, on the ground with a controller, or not even controlling it at all because a computer is. Now, here's where it gets interesting. Because the industry uses a bunch of letters that sound like alphabet soup, and I want you to actually understand the difference. Because you'll hear these in every drone document, every regulation, every job posting. Let's start with UAV, Unmanned Aerial Vehicle. This is just the flying machine itself. The body, the motors, the props, the battery. Just the aircraft. When someone says UAV, they're pointing at the thing in the air. But a drone never flies alone, does it? There's a controller in your hands. There might be a phone or a screen showing you the camera feed. There's a GPS signal coming down from satellites. There's a battery charger back at base. All of that together, the aircraft plus everything on the ground that makes it work, that's a UAS, an unmanned aerial system. So let me make this stick with a simple comparison. Your phone is the device. But your phone plus the charger, plus the SIM card, plus the cell towers, plus the apps, that whole working setup is the system. UAV is the phone. UAS is the phone plus everything that makes it actually useful. When a regulator talks about rules, they almost always say UAS because they care about the whole operation, not just the plastic that flies. Next one, RPA, Remotely Piloted Aircraft. This is a drone where a human is still flying it, just from a distance. There's a real pilot making real decisions in real time. They're just not on board. This term comes mostly from aviation and military circles because they want to make a clear point. A trained pilot is still responsible. When a soldier flies a Predator from a control room in Nevada, while the aircraft is over a desert 10,000 kilometers away, that's an RPA. A human is absolutely flying it. They're just very, very far away. And finally, autonomous UAV. Now this is the spooky cool one. This is a drone where, once you launch it, no human is touching the sticks at all. You give it a mission. Go to these GPS points, photograph this field, come back, and land yourself. And it just does it. It decides. It corrects for wind. It avoids the obstacle. It comes home. So what's the real, practical difference? Let me put it in everyday terms. An RPA is like driving your car. Your hands are on the wheel every second. An autonomous UAV is like a self-driving car. You punch in the destination, sit back, and trust the machine. One has a human in the loop the whole time. The other has a human only at the start. And almost every drone today lives somewhere on a sliding scale between those two. You're any hobby drone? You're flying it, so it's mostly an RPA. But the moment you hit return to home and it flies itself back and lands on its own, congratulations, for those 30 seconds it became autonomous. See how these aren't rigid boxes? They're modes. That's the practical truth most beginners miss. Now, how did we get here? Because drones did not start as fun. Let me tell you the story, and I promise it's better than it sounds. Rewind to 1918, the First World War. There's an engineer named Charles Kettering, same guy, by the way, who later helped invent the electric starter in your car. And the US military asks him to build a flying bomb. Not a missile as we know it. A little wooden and canvas biplane with no pilot that you'd wind up like a clock. It would fly a set distance, the wings would literally fall off on a timer, and it would drop onto the enemy. They called it the Kettering Bug. And honestly, it barely worked. It crashed more than it flew. The war ended before it ever saw real combat. But here's why it matters. For the first time, somebody built an aircraft designed to fly without a person inside it. The idea was born. A flying machine that didn't need a human heartbeat on board. Fast forward to the 1930, Britain. The Royal Air Force needs targets for their gunners to practice shooting at. Real planes are expensive and, have people in them. So they build radio-controlled aircraft to fly around as flying targets. And they give it a wonderful name, the Queen Bee. And here's a little piece of trivia I love. A lot of historians believe that's where the word drone comes from. A drone is a male bee. The queen bee was the target. The smaller pilotless aircraft buzzing around? Drones. The name stuck for 100 years because of a bee joke. Aviation, ladies and gentlemen. Now jump forward to the 1990 and 2000, and the story turns deadly serious. The Predator drone. This is the machine that changed modern warfare. Suddenly, you had an aircraft that could stay in the sky for 20+ hours, beam back live video, and be flown by a pilot sitting safely on another continent. No pilot. At risk. Eyes everywhere, all the time. Every military on Earth took notice, and the drone arms race began. So for almost 90 years, from 1918 to about 2010, drones were basically a military story. Expensive, secretive, scary. And then one company flipped the entire script. A Chinese company called DJI. Around 2013, they did something nobody else had managed. They took all this insanely complex flight technology, the stabilization, the GPS, the cameras, and they packed it into something a teenager could buy and fly in their backyard for a few $100s. They made the drone stable. That's the magic word. Before DJI, flying a multirotor took real skill and a lot of crashes. After DJI, you took it out of the box, pressed a button, and it just hung there in the air, rock steady, waiting for you. They turned a weapon of war into a toy, a camera, a hobby. They democratized the sky. And where are we now? AI drones. Drones that don't just hold position, they recognize you and follow you. They see a tree branch and swerve around it on their own. They map a building in 3D. They fly in swarms of thousands, talking to each other. The brain has caught up to the body. So look at that arc. A crashing wooden bomb in 1918 became a target drone named after a bee, became a weapon that reshaped war, became a toy in your hand, and is now becoming an intelligent machine. 90 years from flying bomb to follow me and fill my vacation. That's the journey. And we're standing right in the middle of the next chapter. Alright, let's get our hands dirty with the actual machines. Because not all drones are the 4-propeller thing on my table. There are basically 3 big families. And the easiest way to understand them is to compare them to aircraft you already know. Type 1. Multirotor. This is your classic drone. Multiple propellers spinning flat, lifting straight up. How does it behave? Exactly like a helicopter. It can take off straight up, hover dead still in the air, spin in place, fly sideways, even fly backwards. Total control, total precision. The catch? It's a hungry beast. Holding yourself up by brute force, fighting gravity every single second with spinning props, burns through battery fast. That's why your hobby drone flies for 25 minutes, not 5 hours. Type 2. Fixed wing. This one looks like a tiny airplane. Wings, maybe a single propeller pulling it forward. And it flies like an airplane. It can't hover. It has to keep moving forward because the wings need airflow over them to generate lift. So why would anyone want a drone that can't stop? Efficiency. A fixed wing glides. The wing does the lifting work, so the motor just has to push it forward, which is far easier than holding the whole thing up. That's why mapping drones and military surveillance drones are usually fixed wing. They can stay up for hours and cover enormous distances. The trade-off is obvious. You can't hover over a single spot, and you need open space to launch and land. So already you see the tension, right? Multirotor. Amazing control, terrible endurance. Fixed wing. Amazing endurance, can't hover. Wouldn't it be great to have both? Type 3. VTOL. Vertical takeoff and landing. And this is the clever hybrid. A VTOL drone takes off straight up like a helicopter props pointing down, then tilts and transitions into flying forward like an airplane on its wings. Best of both worlds. Take off from a tiny space, then cruise efficiently for hours. The perfect everyday comparison? A VTOL is like a hybrid car. A petrol car has great range, an electric scooter is great in the city. The hybrid tries to give you both. VTOL drones try to give you the hover of a helicopter and the endurance of an airplane. They're more complex, more expensive, harder to engineer. But for things like long-range delivery and military reconnaissance, they're becoming the holy grail. 3 families: helicopter, airplane, hybrid. Keep those pictures in your head. Now, since most of you are going to start with multirotors, let's go deeper into this family. Because multirotor just means more than one rotor, and the number of rotors changes everything. Let's count up. Single rotor, one main rotor. This is basically a tiny helicopter. And the most famous example is a jaw-dropper, the Black Hornet Nano. This is a military micro-drone, so small it fits in the palm of your hand, weighs about as much as a few sheets of paper, and soldiers carry it in their pocket. They throw it up, and it silently scouts around the next corner or over the next wall, sending back video, and the enemy never even hears it. A pocket-sized helicopter spy. Single rotor designs are efficient, but they're mechanically complex. Like real helicopters, they need a tail rotor and a complicated head to control them. Tricky to build, tricky to fly. Bicopter. 2 rotors. And here's a fun one. Why did the bicopter basically never catch on? Because 2 motors is just not enough control. With only 2 points of thrust, the drone has to physically tilt its motors with extra mechanical parts just to steer and stay stable. It's wobbly, it's complicated, and it gives you all the headaches with none of the benefits. So engineers mostly looked at it and said, yeah, let's add more motors. Nature did the same thing with insects. By the way, almost nothing useful balances on just 2 points. Tricopter. 3 rotors. Now this one is genuinely interesting from an engineering point of view, and it teaches us something important. 3 motors can lift you fine. But here's the problem. Yaw. Yaw is rotation, spinning left and right, like shaking your head no. On a tricopter, you've got 3 props, and the math doesn't balance out cleanly to control that spin. So tricopters use a little servo motor that physically tilts the rear motor too. Control yaw. It works, and tricopters fly beautifully and smoothly. But that tilting mechanical part is one more thing to break, one more thing to fail. Remember this your problem, because in a second you'll see how the quadcopter solves it with pure elegance and 0 moving parts. Quadcopter. 4 rotors. And this is the king. This is the one on my table. This is 90% of the drones you'll ever see or fly. Why? Because 4 is the magic number. 4 motors give you perfectly balanced lift, perfectly balanced control. And here's the beautiful part. You solve that your problem with no extra mechanical parts at all. Just by spinning some motors a little faster than others, you get full control in every direction. Simple, cheap, reliable, brilliant. The examples here are the famous ones. The DJI Mini Series, tiny, featherweight, designed to slip under the strictest weight regulations so beginners can fly almost anywhere. The DJI Air Series, the sweet spot, more camera, more power, still portable. The DJI Mavic Series, the foldable pro-grade workhorse that put a cinema-quality camera in a backpack. And on the wild end, FPV racing drones, where pilots wear goggles, see through the drone's eyes, and rip through courses at over 100 kilometers an hour. Same for rotor layout. Completely different soul. One's a flying tripod, the other's a flying roller coaster. Now let's go bigger. Hexacopter. 6 rotors. Why would you need 6? One word, and it's the most important word in professional drones: redundancy. Let me paint you a scene. You're a film crew. You've strapped a $40,000 red cinema camera under your drone. You're flying it over a crowd at an outdoor concert. You've got one shot at the scene. Now, what happens if a motor fails midair? On your little quadcopter, a motor failure is a disaster. You've lost one of 4 corners of lift. The drone immediately becomes unbalanced and flips, and it falls out of the sky like a stone. $40,000? Gone. Worse, it falls into a crowd. On a hexacopter, one motor dies, and the flight controller, the brain, instantly goes, "No problem, I've got 5 more." It redistributes the power across the remaining motors and keeps flying, or at least limps down to a safe, controlled landing. That single extra layer of safety is everything when there's expensive gear or people below. That's why you'll find 6 rotors on the DJI Matrix 600 on professional cinema rigs carrying those red cameras, and on industrial inspection drones crawling over oil refineries and power lines where a crash isn't just expensive, it's dangerous. Redundancy. Write that down. It's the reason professionals add motors. Octocopter. 8 rotors. Now we're at the top of the food chain. Why 8? 2 reasons, and they're the same 2 reasons rolled into one big machine. First, raw lifting power. 8 motors can hoist heavy payloads. Second, even more redundancy. You could lose a motor, maybe even 2, and still fly home safely. The poster child here is the FreeFly Alta X, an absolute beast of a flying platform that the film industry trusts with cameras worth more than a car. We're talking heavy lift cinema setups, large agricultural drones hauling tanks full of pesticide over fields, industrial logistics drones moving real cargo. So why do movie productions hand their most expensive equipment to an octocopter and sleep fine at night? Because they're not paying for the 8th rotor to go faster. They're paying for insurance. They're paying for the night the director gets the perfect golden hour shot, a motor coughs and dies, and the drone just shrugs and keeps filming. When the gear under your drone costs more than your house, you do not gamble on 4 motors. You buy 8. Redundancy, again. See the pattern through this whole family? As you go up in rotors, you trade simplicity and cost for power and safety. Beginners and racers love quads. Professionals carrying valuable things climb to 6 and 8. There's a reason for every motor on every drone. It's never random. Now, before we talk about how India sorts drones into weight classes, and I have to stop and ask a question almost nobody asks. Who's actually in charge of the sky? Because here's the thing. The sky isn't lawless. You can't just buy a drone, walk outside, and send it screaming up to 10,000 feet next to a passenger jet full of people. Right? Of course not. So who decides the rules? And here's what's fascinating. Every country has its own air traffic cop. And if you ever want to fly drones professionally, or sell them, or even travel with one, you need to know who these players are. Let me introduce you to the Big 6. United States, the FAA, the Federal Aviation Administration. These are the people who run all of American airspace, manned and unmanned. Every passenger jet, every drone, all of it. When they say a drone must stay below 400 feet and away from airports, the entire US drone industry obeys, because the FAA controls the sky. European Union, ESA, the European Union Aviation Safety Agency. One agency, dozens of countries. ESA's whole trick is harmonizing the rules so a drone pilot certified in France can understand the rules in Germany or Spain. Imagine the chaos if every European country had totally different drone laws. ESA exists to prevent exactly that. United Kingdom, the CAA, the Civil Aviation Authority. Britain's own aviation regulator, especially relevant after they left the EU and needed their own clear drone rulebook. Same job, keep the British skies safe and orderly. Australia, CASA, the Civil Aviation Safety Authority. Australia was actually one of the earliest countries in the world to write proper commercial drone rules. Big country, lots of remote land, lots of agricultural and mining drone use, they had to get organized early. China, the CAC, the Civil Aviation Administration of China. Now this one's important, because China is where most of the world's drones are built. Remember DJI? So the CAC regulates not just flying, but a massive manufacturing ecosystem. And India, the DGCA, the Directorate General of Civil Aviation. This is our regulator. The DGCA writes the drone rules for India. And they've been busy, because India's drone industry is exploding in agriculture, surveying, and delivery. Now, full name, country, job. You've got those. But let me answer the deeper question, the one that actually matters. Why do these agencies exist at all? Why do we need rules for what looks like a toy? Why registration exists? Think about it. If a drone falls on someone's car or flies somewhere it shouldn't, how do you find out whose it was? Registration is like a number plate for your drone. It connects a flying object to a responsible human being. No accountability without identity. Why pilot certification exists? Would you let someone drive a car on the highway who would never had a single lesson? No. As drones get bigger and fly in busier places, the people flying them need to actually understand airspace, weather, and safety. Certification makes sure the pilot isn't a complete danger to everyone around them. Why BVLOS operations are regulated. And let me unpack that term, because it's huge. BVLOS means beyond visual line of sight. Normally, you have to be able to see your drone with your own eyes. But the real future, delivery, long-range inspection, large-scale mapping, needs drones that fly far away, out of sight, controlled by computers and cameras. That's incredibly powerful and incredibly risky, because now there's a flying machine miles away that the pilot can't even see. So regulators are extremely careful about who's allowed to do it and how. BVLOS is basically the locked door between drones as toys and drones as a real transport industry, and every regulator on Earth is figuring out how to open it safely. And underneath all of it, why do governments care about safety so much? One word, people. The sky is shared. Up there you've got airplanes with hundreds of passengers, helicopters, and on the ground you've got crowds, cars, houses, hospitals. A 2-kilogram drone hitting a jet engine or falling on a child's head is a genuine catastrophe. These agencies aren't there to ruin your fun. They're there so that the sky stays safe enough that all of us, hobbyists, pilots, passengers, people on the ground, can share it without dying. That's the real job. Okay, now that you understand who's in charge and why, let's look at how India actually sorts drones. So the DGCA, like most regulators, sorts drones by weight. And it makes total sense, right? A drone the size of your palm is just not the same threat as a drone the size of a dining table. Heavier means more damage if it falls, more energy, more risk. So heavier drones get stricter rules. 5 categories. Let's run through them with real examples. Nano. Up to 250 grams, that's it. A quarter of a kilo, lighter than a glass of water. And this category is special because in India and in many countries, the rules for nano drones are the most relaxed. Why? Because something this light, even if it hits you, is unlikely to do serious harm. This is exactly, and I mean exactly, why the DJI Mini weighs just under 250 grams. It's not a coincidence. DJI deliberately engineered it to sneak under that nano limit, so beginners and travelers face the fewest restrictions. Smart business, smart engineering. Micro. From 250 grams up to 2 kilograms. This is where a huge chunk of hobby and prosumer drones live. Your DJI Air, many Mavics, lots of camera drones. Heavier, more capable, more camera. And now the rules tighten a bit. You're starting to carry enough mass that the regulator pays attention. Small, from 2 kilograms up to 25 kilograms. Now we're into serious working machines. Many professional cinema drones, survey drones, and the smaller agricultural sprayers land here. These aren't toys anymore. These are tools that earn money, and the rules reflect that. Medium, from 25 kilograms up to 150 kilograms. This is heavy lifting territory. The big agricultural spraying drones that haul large tanks of liquid across farmland often sit in this class. Big delivery drones too. At this weight, you're operating a genuine aircraft, and certification and permissions get serious. Large, above 150 kilograms. And now we've left Hobbyland entirely. This is the domain of military drones and major commercial cargo and surveillance aircraft. A drone this big is treated almost like a manned aircraft, because in terms of mass and risk, it basically is one. The Predator we talked about earlier, that's not a drone you fly in a park. That's large category aviation hardware. So look at the whole ladder. A 249-gram DJI Mini in your backpack and a 1,000-kilo military surveillance aircraft are both technically drones, but the DGCA treats them completely differently. And now you understand exactly why. Weight equals risk. Risk equals rules. The heavier you fly, the more the sky demands of you. Now, normally this is the part of a lesson where someone reads you a boring list of definitions and your eyes glaze over. Not here. Let me just use these words in a story and you'll absorb them without even trying. Picture this. You're standing in an open field with your brand new drone. The first thing you do is look up at the sky and the breeze, and you think about your ceiling. That's the maximum height you're allowed or able to fly. Go above your ceiling, and you're either breaking the law or running out of air for your props to bite into. So you keep it sensible. You take off, and the drone climbs and stops in midair, holding perfectly still. That's a hover. The drone fighting gravity to a perfect draw, neither rising nor falling. Beautiful. It's the most basic skill and weirdly one of the most satisfying. You start flying it away from you, and your friend asks, how far can it go? Well, that depends on your range, how far the drone can travel and still hear the controller. Fly past your range and the link breaks, and that's when your drone had better be smart enough to do its return to home, automatically turning around and flying back to where it took off. RTH has saved more lost drones than anything else ever invented. Then a gust of wind hits, and the drone drifts. You notice it doesn't just blow away like a balloon. It fights back, holding its spot. That fight, that ability to stay steady and resist getting knocked around, is its stability. And what's giving it that stability? Sensors and a brain we're about to meet. You glance at your screen and see the battery dropping, and you start thinking about endurance. How long this thing can actually stay airborne on one charge. 20 minutes? 25? That number runs your whole flight. And trust me, you learn to respect it fast. And finally, the wind picks up to the edge of what your drone can handle. It's wind resistance. The maximum breeze it can fly in before it just can't fight anymore and starts losing the battle. See what just happened? Ceiling, hover, range, return to home, stability, endurance, wind resistance, 7 terms. And you didn't memorize a single definition. You just went flying with me. That's how you learn vocabulary. By living it. Right. Now we get to the physics, the real heart of this whole video. And here's the wonderful secret. Every single thing that flies, a drone, a jumbo jet, a bird, a paper airplane, obeys the exact same 4 forces. Master these 4, and you understand all of flight. 4 arrows. That's it. Force 1. Lift. This is the upward force, the hero of the story. Lift is what pushes the aircraft UP, fighting gravity. On your drone, lift comes from the propellers. On an airplane, it comes from the wings. No lift, no flight. Simple as that. Force 2. Weight. This is the villain, and it never sleeps. Weight is gravity pulling everything straight down. The drone, the battery, the camera, all of it. Weight is constant, it's relentless, and the entire game of flight is generating enough lift to beat it. Here's a question to make it real. When does a drone hover perfectly still? Exactly when lift equals weight. The up force and the down force cancel out to a perfect tie, and the drone just hangs there. Make lift bigger than weight, it climbs. Let lift drop below weight, it descends. Hovering is literally a tight score between two opposing forces. Isn't that a lovely way to think about it? Force 3. Thrust. This is the forward push. What moves you in the direction you want to go? On a jet, it's the engines blasting backward. On your drone, here's the clever part. To go forward, the drone tilts itself slightly forward. And now some of that propeller force points forward instead of straight up. That's your thrust. Let me make thrust physical for you. Have you ever stuck your hand out the window of a moving car? Of course you have. Now, tilt your hand up slightly, palm angled into the wind, and what happens? Your whole arm gets pushed back and up. You can feel the air shoving it. That push is exactly the kind of force a propeller creates, just controlled and aimed. Your hand became a wing. You've been doing physics experiments out of car windows your whole life and didn't know it. Force 4. Drag. This is the invisible enemy, air resistance. The friction of pushing through the atmosphere. Drag always fights your motion. It's constantly trying to slow you down. Anything moving through air feels it. The perfect example? A motorcycle. When you ride slowly, you barely notice the air. But twist the throttle and hit 100 kilometers an hour, and suddenly the wind is screaming past you, trying to rip you off the seat, pushing back hard against your chest. That push is drag. The faster you go, the harder drag fights you. It's the reason racing motorcyclists tuck down flat. They're hiding from drag. And it's why drones, jets, and even cyclists are shaped smooth and sleek. Every curve is a little argument against drag. So there it is. 4 forces, locked in a constant tug-of-war. Lift versus weight, up versus down. Thrust versus drag, forward versus backward. Every flight you've ever seen is just these 4 numbers shifting around. Want to climb? Beat weight with lift. Want to speed up? Beat drag with thrust. Want to hover? Make it all a perfect tie. That's flight. That's the whole secret. And one more time, throw a paper airplane across the room. In that 2-second flight, all 4 forces were at play. Lift held it up, weight pulled it down, your throw gave it thrust, and drag slowed it until it lost the fight and glided to the floor. 4 forces in a toy made of paper. The sky doesn't care if you're a Boeing or a paper plane. Same rules for everyone. So lift is the hero. But how does a spinning piece of plastic actually create it? This is where most explanations either lie to you or bore you, and I want to do neither. Because the truth is, there are 2 explanations, and both are right, and engineers use both. Explanation 1. Bernoulli's principle. Here's the idea. A propeller blade isn't flat. It's shaped, curved on top, flatter on the bottom. As it spins, air rushing over the curved top has to travel faster than the air underneath. And here's Bernoulli's beautiful, slightly weird rule. Fast-moving air has lower pressure. So you get low pressure on top of the blade, higher pressure underneath. And that pressure difference sucks and pushes the blade upward. Multiply that across spinning blades, and you get lift. Now, I know what you're thinking. Faster air has lower pressure? That sounds made up. So let me prove it to you right now. With nothing but 2 sheets of paper. I want you to actually do this. Pause the video if you have to. Take 2 ordinary sheets of paper. Hold them up vertically, hanging down, parallel to each other, with a small gap between them, maybe a few centimeters. Now, common sense says, if I blow air into that gap, the papers should fly apart, right? The air should push them away from each other. That's the obvious answer. Watch what actually happens. I blow air straight down the gap between them, and the papers snap toward each other. They come together, the exact opposite of what you'd expect. Why? Because by blowing, I made the air between the sheets move fast. And fast air, Bernoulli, is low pressure. Meanwhile, the air on the outside of the sheets is still calm, normal, high pressure. So you've got high pressure on the outside pushing in, low pressure in the middle, and the sheets get shoved together by the surrounding air. The papers didn't move because of my breath pushing them apart. They moved because I created a low pressure zone and the higher pressure around them pushed them in. That, right there, is exactly what happens around a propeller blade. Fast air, low pressure on one side. Slow air, high pressure on the other. And the blade gets pushed toward the low pressure side, upward. You just felt Bernoulli's principle with 2 sheets of paper. That's the trick hiding inside every wing and every prop on Earth. Explanation to Newton's third law. But there's a second, blunter way to see it, and it's just as true. Newton's third law. For every action, there's an equal and opposite reaction. A propeller is, basically, a fan. It grabs a huge column of air and throws it downward. And if the prop throws air down, then by Newton, the air throws the prop UP with equal force. Push the air down, you get pushed up. It's that simple. Stand under a flying drone and you can feel the downwash. That's the air it's throwing at the ground to hold itself up. So which explanation is correct? Bernoulli or Newton? And here's the answer that separates a real engineer from someone who just memorized one line in a textbook. They're both correct. They're 2 languages describing the same event. Bernoulli describes it through pressure differences. Newton describes it through air being thrown downward. Same lift, 2 viewpoints. And here's how engineers actually use both when designing a propeller. They use Bernoulli to perfect the shape, the exact curve of the blade, the airfoil. So the air flows smoothly and creates that pressure difference efficiently without turning into turbulent chaos. And they use Newton to think about the brute force. How much air can this blade physically grab and hurl downward per second? Shape and force. Pressure and momentum. A great propeller is a marriage of both ideas. That's why prop design is real engineering and not just make a fan. Beautiful, isn't it? Now that you know why a prop makes lift, let's actually look at one. Because the anatomy matters more than you think. Holds up a propeller. Run your eye along the blade. The front edge, the one that slices into the air first as it spins, that's the leading edge. It's usually rounded and smooth, designed to cut cleanly into the air. The back edge, where the air leaves the blade, is the trailing edge, usually thinner and sharper, so the air can flow off cleanly without making a mess of turbulence. The cross-section shape of the blade, that curved on top, flatter on bottom profile we just talked about, that's the airfoil. That's the magic shape doing the Bernoulli work. Now to numbers define almost everything about a prop's personality. First, diameter, how wide the prop is, measured tip to tip across the full circle it sweeps. Bigger diameter grabs more air, which generally means more lift and more efficiency. But it also takes more power to spin and responds more slowly. Second, and this is the one beginners always misunderstand, pitch. Pitch is the angle of the blade, and here's the best way to grasp it. Pitch is the theoretical distance the prop would move forward in one full rotation, like a screw going into wood. A high-pitch prop is like an aggressive screw. It takes a big bite of air with every turn and tries to move a long way forward. A low-pitch prop takes a gentle, shallow bite. And finally, number of blades. 2 blades, 3 blades, sometimes more. More blades grab more air and give more grip and thrust, but they also create more drag and burn more power. Fewer blades are more efficient, but grippier props are sometimes worth it. It's always a trade-off. Everything in this hobby is a trade-off. So let me make pitch real with a question. Why does a racing drone use totally different props than a smooth cinematic drone? Think about a bicycle with gears. A high gear, like high pitch, gives you huge top speed, but it's brutal to get moving and it exhausts you. A low gear, like low pitch, gets you moving instantly and climbs hills easily, but it tops out slowly. A racing drone wants raw speed and savage acceleration, so it uses aggressive, high-pitch props, big bites of air, maximum thrust. Who cares about battery life when the race is over into minutes? A cinematic drone wants smoothness, efficiency, and long flight time to get the perfect shot. So it uses gentler, low-pitch props that sip power and respond softly and steadily, no jerky movements to ruin the footage. Same physics, completely. Different tuning, because they want completely different things. Change the pitch, and you change the entire soul of the drone. Okay, now we need to talk about how a drone moves in 3 dimensions. And there are 3 magic words: pitch, roll, and yaw. These confuse everyone at first, until I show you the trick I'm about to show you. Because you already know all 3. You do them with your own head. Ready? Use your own body with me. Pitch. Nod your head, yes. Up and down, tilting forward and back. That's pitch. When a drone pitches, it tips its nose down to fly forward, or tips its nose up to fly backward. Pitch is yes. Nodding forward to go forward. Yaw. Now shake your head, no. Left and right. Rotating, turning. That's yaw. When a drone yaws, it spins in place, rotating to face a new direction without actually moving anywhere. Yaw is no. Turning to look around. Roll. Now tilt your head sideways toward your shoulder, like you're trying to touch your ear to your shoulder. That leaning, tilting sideways motion, that's roll. When a drone rolls, it tips left or right to slide sideways through the air. Roll is leaning over. Let me say it one more time, because I want this burned into your memory forever. Pitch is nodding yes. Yaw is shaking no. Roll is leaning your head sideways. Yes, no, sideways. You will literally never forget it now, because you'll always have your own head to check against. Every fighter pilot, every drone pilot, every astronaut uses these exact 3 words, and now you own them too. Here's the part that genuinely blew my mind when I first understood it. A quadcopter has no moving parts for steering, no flaps, no tilting motors, no rudders, nothing mechanical like an airplane. It does everything, every move in the sky, just by changing how fast each of its 4 motors spins. That's it. Differential motor speed. Let me walk you through every move. First, an important detail. On a quad, the motors don't all spin the same direction. To spin clockwise, to spin counterclockwise, arranged diagonally. Remember that it's the key to the whole magic trick, especially yaw. Hover. All 4 motors spin at the exact same speed, fast enough that total lift perfectly equals weight. Everything's balanced, nothing's tilted, and the drone just hangs there, frozen in the sky. Perfect eye. Beautiful. Climb. Want to go up? Easy. Speed all 4 motors up equally. Now lift beats weight, and the whole drone rises straight up, staying perfectly level. Want to descend? Slow all 4 down equally, weight wins, and it sinks gently straight down. Pitch, flying forward. Here's the clever bit. To fly forward, the drone speeds up the 2 rear motors and slows down the 2 front motors. The back lifts higher, the front dips lower, the whole drone tilts nose down, and now a chunk of that propeller thrust points forward, and off it flies. To fly backward, just do the opposite. Speed up the front, slow the back, tip nose up, fly back. Roll, sliding sideways. Same idea, but left and right. To slide right, speed up the 2 left motors and slow the 2 right motors. The drone tilts to the right and slides right. Tilt left to slide left. Notice it's the same principle as pitch, just rotated 90 degrees. Yaw, spinning in place. And here's the elegant solution to that problem the tricopter struggled with. Remember? No servo, no moving part. Here's how a quad does it. When a motor spins one way, it creates a tiny twisting reaction in the opposite direction, Newton again. Normally the 2 clockwise motors and 2 counterclockwise motors cancel each other's twist out perfectly, so the drone doesn't spin. But if you speed up the 2 clockwise spinning motors and slow down the 2 counterclockwise ones, you unbalance that twist. Suddenly there's a net rotational force, and the whole drone slowly spins in place. It yaws. No moving parts. Just smartly unbalancing the spin of the motors. The tricopter needed a mechanical servo to do this. The quadcopter does it with pure cleverness. That's the engineering beauty of four rotors. So step back and look at what we've got. Climb, descend, forward, back, left, right, and spin, every possible movement in three-dimensional space, all controlled by nothing more than four motors speeding up and slowing down in different combinations, hundreds of times per second. No gears, no flaps, just math and motors. It's honestly one of the most elegant control systems humans have ever built. And it raises one terrifying question. Who's doing all that math? Because here's a secret that should frighten you a little. A quadcopter is naturally unstable. Completely. On its own, with no brain, a quad cannot fly for even half a second. It would instantly tip, flip, and smash into the ground. It is fundamentally, physically unstable. So how does it hover so calmly? Let me show you with a pencil. Picks up a pencil. Try to balance this pencil straight up on the tip of your finger. Go on. What happens? It falls. Instantly. Now, can you actually balance it? Yes. But only if you constantly move your finger, making tiny corrections, left, right, forward, back, faster than you can even think about it. The moment you stop correcting, it falls. Balancing a pencil isn't a state. It's a furious, never-ending stream of micro-corrections. That is exactly what a drone is doing every millisecond it's in the air. It is balancing a pencil, except it's balancing itself in three dimensions hundreds of times per second. And the finger doing all those corrections is a tiny brain called the flight controller. Let's meet the team inside it. First sensor, the gyroscope. Its one job is to measure rotation, how fast the drone is tipping or twisting in any direction. It's the inner ear of the drone. The instant the drone starts to tilt even a hair, the gyro screams, "Hey, we're tipping right." Second sensor, the accelerometer. Its job is to sense acceleration and, crucially, gravity, so it always knows which way is down. It's the drone's sense of balance, the thing that knows up is up. Together, the gyroscope and accelerometer are usually packed into one little chip that tells the drone its exact orientation in space at all times. Then the boss, the flight controller. This is the brain, a tiny computer reading those sensors hundreds, sometimes thousands of times every second, comparing what's happening against what the pilot asked for, and barking orders to the four motors. Speed this one up, slow that one down, now, faster, correct, correct, correct. And the genius math it runs is called a PID controller. Don't panic about the letters. PID is just a brilliant way of answering three questions, constantly. How far off am I right now? How fast am I drifting off? And how have I been trending over time? It blends those three answers into the perfect sized correction, not too weak, not too violent, just right. Too aggressive and the drone shakes and oscillates. Too gentle and it drifts and wobbles. A well-tuned PID is the difference between a drone that hovers like it's nailed to the sky and one that bounces around like a nervous bird. Tuning PID is half the art of building a good drone. So here's the big picture, and I really want this to land. Without the flight controller, your beautiful four-rotor machine is just a pencil that nobody's balancing. It flips over and dies in a fraction of a second. Every stable, calm, gorgeous hover you've ever seen is actually a tiny computer fighting a desperate, invisible, 1,000 times a second battle to keep that pencil upright. The calm you see is a lie. Underneath, it's pure, controlled chaos. And that, to me, is the most beautiful thing about drones. Alright, let's talk about power and how engineers measure whether a drone is a sluggish truck or a screaming rocket. The magic number is the thrust-to-weight ratio, or TWR. It's exactly what it sounds like. Take all the thrust your motors and props can produce at full throttle and divide it by how much the drone weighs. That's your TWR. Let's make it concrete. If your drone weighs 1 kilogram and your motors at full power can push 2 kilograms of thrust, Your WR is to 2:1. You've got twice as much push as weight. So why does this number matter so much? Think about it. If your TWR were exactly 1:1, thrust just barely equals weight. Your drone could only just hover. It would have zero power left over to climb, fight wind, or maneuver. It would be gasping at full throttle just to stay still. Useless. So you always need more than 1:1. The question is, how much more? And this is where the world splits in two. A cinematic drone, the smooth camera platform, typically runs a TWR of around to 2:1. That's plenty. It gives gentle, controlled, graceful movement, smooth acceleration, no jerkiness, and great efficiency for long flights. You don't want a camera drone to be twitchy and explosive, you want it calm and cushiony, like a luxury car gliding down the highway. Smooth footage demands a relaxed, well-mannered drone. Now a racing or freestyle drone? These lunatics run TWRs of 8:1, 10:1, sometimes more. 10 times more thrust than weight. What does that feel like? It means the drone can rocket from a standstill to over 100 kilometers an hour in a couple of seconds. It can flip, dive, and slam through gaps with insane, brutal acceleration. It's not a luxury car. It's a fighter jet with no manners. That ridiculous power to weight is exactly why FPV racing footage looks so impossibly fast and aggressive. So next time someone shows you a drone, ask them one question. What's your thrust to weight? To 2:1, you've got a smooth, civilized cinema bird. 8 or 10:1, buckle up. Because that thing is a rocket with propellers. Same four forces, wildly different personalities. And it all comes down to one ratio. So we keep talking about thrust. This motor makes 2 kilos of thrust. That prop makes more. But how does an engineer actually know that? Do they just guess? Stick a finger in the wind? No. They use a beautiful little piece of workshop equipment called a thrust stand. And I want to turn this into a proper workshop demo in your head. Here's the setup. You clamp a single motor onto the stand. You bolt a propeller onto the motor. And underneath, the stand has a sensor called a load cell. And a load cell is just a precise little device that measures force, that measures push. Then you spin the motor up, the prop starts blasting air. It tries to lift off, and the load cell measures exactly how much thrust it's producing in grams in real time on a screen. And here's the everyday comparison that makes it click instantly. A thrust stand is basically a bathroom weighing scale, flipped on its side. Think about it. When you stand on your bathroom scale, your weight pushes down on it, and it reads the force. A thrust stand does the same thing, except the propeller is pushing sideways or up against the load cell, and the load cell reads that push as a number. It's a weighing scale that measures the strength of your propeller instead of the weight of your body. Same idea, rotated. So what does an engineer actually do with it? They test combinations. They'll take one motor and try 5 different propellers on it. Different diameters, different pitches, different numbers of blades, and measure. Which prop gives the most thrust? Which one is most efficient, giving the most thrust per watt of battery power? Which combination runs coolest, so the motor doesn't burn out? They build a whole table of data, all from spinning props on a stand on the bench. And here's why this matters. The real lesson. You test on the stand so you don't discover the problem in the air. Because a motor and prop combo that's too weak means a drone that can barely take off. One that's too power hungry means a drone that dies in 5 minutes. One that runs too hot means a motor that melts itself mid-flight and drops your aircraft out of the sky. Would you rather find that out safely on a workbench with the drone bolted down? Or 200 feet in the air over a crowd? Exactly. Real engineers don't guess and pray. They measure, they test, they know, and only then do they fly. The thrust stand is where confidence comes from. It's the difference between I think this'll fly and I know this'll fly. Okay, take a breath. Look at how far you just came. When we started, a drone was just a mysterious flying thing with propellers. Now you know what a drone actually is. UAV, UAS, RPA, autonomous, and the real difference between them. You know the story, from a crashing wooden bomb in 1918, through the Queen Bee, the Predator, the DJI revolution, all the way to today's AI. Drones. You know the three families, Multirotor, Fixed Wing, and VTOL, and why each one exists. You walk through the entire Multirotor family, from the pocket-sized Black Hornet all the way up to Etrotor Cinema Beasts, and, most importantly, you understand why professionals add motors, redundancy, safety, lift. You know who policies the sky around the world? The FAA, ESA, CAA, CASA, CAC, and our own DGCA. And why those rules exist at all. You can sort any drone into its DGCA weight class and explain the logic behind it. And then we got to the good stuff, the physics. You now understand the four forces: lift, weight, thrust, and drag, locked in their eternal tug-of-war. You proved Bernoulli's principle with 2 sheets of paper. You learned that propellers use both Bernoulli and Newton. You can read a prop, leading edge, trailing edge, airfoil, pitch, diameter, and explain why racers and filmmakers choose different ones. You'll never forget pitch, roll, and yaw, because they're just nodding yes, leaning sideways, and shaking no. You know how a quad steers with nothing but 4 motor speeds. You understand the flight controller is balancing a pencil 1,000 times a second with a gyro, an accelerometer, and PID math. And you can talk thrust-to-weight ratio and thrust stance like an engineer. That is a lot. That's a real foundation. And let me tell you something honestly. If you genuinely understood what we covered today, you are already miles ahead of most people who simply buy a drone, charge it, and chuck it into the sky with no idea what's holding it up. You don't just own a drone now. You understand one. That's a completely different thing. And it changes everything about how you'll fly, build, and troubleshoot from here on. So where do we go next? In the next mission, we stop talking about drones from the outside, and we crack one wide open. We're going to take a drone apart on this very table and explore every major component inside it. The motors, the ESCs, the flight controller, the battery, the receiver, all of it. If today was how a drone flies, next time is what a drone is made of. So here's what I need you to do. If this made the physics finally click for you, hit that subscribe button and turn on the bell, because you do not want to miss Mission 02. Drop a comment and tell me the one thing that surprised you most. Was it the 2-sheet paper trick? The pencil balancing flight controller? The bee that gave drones their name? I read every single one. And if you've got a friend who thinks drones are just toys, send them this video. Let's change their mind together. This has been Mission 01 Chapter 01 of Droneverse. The sky's not the limit anymore. It's the classroom. I'll see you in the next one. Keep looking up. Droneverse, Mission 02, Inside the Machine. Coming soon.